Hi, y'all. Back for another round of physics. And today we're going to start moving on into a second layer of mechanics, if you will. And namely, we're going to start working with what's called energy. So I'll say energy. Energy. And coupled along with this is the idea of work. Work. Now, this isn't any new physical concept. Essentially, as we'll see in this video, it's just a recasting of some old ideas that we are already familiar with. The upshot with this, though, is that energy and work are both what we call scalars. Scalars. So instead of having to think about vectors and doing free body diagrams and breaking into components and working our way through that way, energy and work allow us to actually think of problems in terms of scalars, so just a single number, and solve them that way. Now, that's obviously one of the benefits. One of the disadvantages is that this is only good for deriving particular pieces of information. So generally, if you're dealing with something like height, speed, height or speed, it's probably better to go into the energy realm to actually get those answers. If you're asked for something like time, how long it takes for a process to occur, then you're probably better off still dealing with forces. Now, that's not to say that you can't get, for example, height or speed dealing with forces. It's just that it's easier to do it from the energy perspective. Okay. Similarly, I would have to think a little bit more about how to do something like answering time. My guess would be is that you'd probably end up having to apply some sort of kinematic equation. It's not an effective way. If you're asked for finding how long it takes for something to occur, it's not effective to be thinking about energy or work. So, okay. Well, the first thing that we should get into is where do these concepts actually come from? And you might not be surprised to find out that we're going to start with Newton's second law. So starting off with Newton's second law, we have the net force is equal to the mass times the acceleration. And let me for a minute consider just the x component. So I'm just going to consider the x component during this derivation. But we'll see that there's nothing special about the x component. We'll redo it for the y, the z, and you'll end up with the same answer. So starting with that, let's say, hey, we've got a net force, and we're thinking about mass times acceleration in the x direction. And the first thing I'm going to do is let me go ahead and write the acceleration in terms of changes in velocity and time. So I have something that says the net force, actually I'll just leave it as net, there we go, equals our mass times our acceleration, our change in velocity, change in the speed in the x direction per unit time. There we go. So the x component of the velocity. And now I'm going to do the favorite mathematical, magical trick. I'm going to multiply by 1. So, but I'm going to present 1 in a very interesting manner. Say f net is equal to m. And here what I'm going to do is I'll do delta v x over delta x times our change in x over our change in time, delta t. Okay. And of course now we'll say, hey, wait a minute, I know what this is. This piece right here, delta x over delta t, that's defined as, sorry, accidentally scrolled somehow, that's defined as v average, my average speed. So I can rewrite this as f net equals m, mass, times my change in speed, change in position, times my v average in the x direction. But wait, there's more. Now I'm going to substitute in values for delta v and v average. I'll also move the delta x to the other side for convenience. So I have f net delta x equals my mass change in, so I have my final minus my initial, and then my V average is final plus initial, all divided by 2. Let's go ahead and go to the top of the screen here. So I have all of this. Let me go ahead and FOIL. So I get F net delta x equals 1/2. I have an m. And then I'll just go ahead and FOIL this. I have V final squared minus V initial squared. Cool. So what's going on here? We see that we started off with the x components, the x component of Newton's second law, and we've now been able to rearrange it in a different manner. Just express it instead of terms of accelerations, we're expressing it as a change in, I want to say a change in speed, but related to the speeds. So we look at this and we say, well, if we believe that Newton's second law is correct, this is completely analogous, right? Here, we start off with Newton's second law, we derive this expression. So long as we believe that Newton's second law is correct and that our definitions of average acceleration average velocity and changes in velocity, as long as those are correct, then this expression is perfectly general, which is pretty spiffy. So now we're at a point where we would like to redefine new physical quantities. So over here, we have this net force times delta x. So a displacement times a net force. And so we define this as a new physical quantity. We're going to define that as being equal to work. Okay. Over here, we see that we have some new physical quantity, okay, that's related to the motion, the movement, I'll say motion, of the object. In fact, the speed of the object is the observable, it's the motion. And so we will, if you're familiar with the term, kinetic is kind of the official term that means moving. And so this 1/2 mv squared, this quantity, we're going to define that as being kinetic energy. So what are we dealing with here? If I take this expression and I rewrite in terms of these new physical quantities that we've just defined, we have something that says work, W, is equal to a change in kinetic energy of the object. Which is pretty cool. Now notice, first of all, work is a scalar, it's just a number, and kinetic energy is just a number. And sometimes this is referred to as the work kinetic energy theorem. So sometimes you'll see it referred to as the work kinetic energy theorem. Okay. Now, please note there's a couple of things I should point out. And first of all, notice that I did this for the x component. Okay. You could have similarly done this for the y component or the z component. Okay. Could have done the exact same process. So in that regards, we should say that the total work, I'll say the total work done, is simply the work that was associated with this x component. So it's not a vector, but I want to say that you get 3 pieces from the work. You get one from the x component, one from the y component, and one from the z component. So looking at the motion changes in kinetic energy going in the x direction, the y direction, and the z direction. What I really want to say is that we have a simple, nice way of actually figuring out this total work. Now, yes, you could do it this way if you wanted. You could consider the x direction and the changes in kinetic energy. You could consider the y direction, and you could consider the z direction, and then just add them up. But this is probably not the most useful way of doing it. Why don't we take advantage of some of the mathematical properties that we've developed earlier? And how this is that we would say work is defined as being the dot product of our vector force with our displacement. And this would be a much faster way of calculating the quantities. Okay, so this is how work is defined. Let's go ahead and let's get rid of all that. And I'll rewrite this again. Oops, excuse me. Get rid of that. So we'll say, okay, well, the definition of work is F dot dr, delta r. Okay. Or if you want, this is the algebraic definition. This assumes that your force is fairly constant, remains constant during your displacement. And you say, well, why does that have to be? Well, remember, we used the V average, the definition of V average, in order to arrive at this expression. Okay? And the minute that we use the arithmetic average, that means the minute that we use this arithmetic average, that means or implies that the acceleration is constant, which implies that our net force has to be constant. Okay. Now and remember, it's constant over this displacement delta r. But what happens, you say, wait, Greg, what happens if I have a mean force? Well, that's a perfectly good question. And how we deal with a mean force? Well, if you have a mean force, you would just need to take these delta r's and make them small enough that the force is approximately constant. And then you just have to take a summation. In other words, if your force is not constant over the entire displacement, simply break your delta r's up into smaller chunks so that your force is constant, and then you just have to take the summation. Of course, those of you that are familiar with the calculus notation, we could instead write this in terms of calculus as being work is the integral of F dotted into dr, the infinitesimal displacement. And this would be the most generic definition that you have. And this third one. That allows you to do constant forces. That allows you to do mean forces, ones that vary. This would be the best way to go at it. And we'll take advantage of this. Often we'll see this F delta R coming into play. So that's one warning, or that's one thing. The other thing that I should point out, and we should go back to this F net equals MA. And this is subtle, but it's something that's worth noting now, is when we were actually doing Newton's second law problems, you would think of boxes, for example, you think of boxes on tables, or, cars driving. So little cars driving, or maybe people jumping in the air. Okay. So you'd have all of these different situations. And the thing I would like to ask, or at least point out to you now, since we haven't talked about it very much, is when we want to model our system, okay, so whether it be a box on a table or a car on a road, or a person jumping, when we actually want to model that system, What did we actually model it as, conceptually speaking? Or if it helps you, start thinking about how do you actually go about solving a Newton's second law problem. You said the system, the surroundings, you drew a diagram, and then you would do what's called a free body diagram. So you do the physical situation, your system and surroundings, and then you'd say, okay, well, let me draw a free body diagram to visualize the forces. And the question is how did you conceptualize the system? Got it? When we're doing a free body diagram, we would conceptualize the system as simply being a point particle, right? It's not by accident that I would not get very fancy. So we'd model system as point particle. Okay. Now here's the next question for you. If we're modeling the system as a point particle, where is the best place to think of that point particle as being located? For example, if I want to model this box as a point particle, where would it make the most sense for you to actually think about the location of the point particle? Hopefully you're running through. Hopefully you've got it, but you said, okay, well, do you think of it at the top of the box? Do you think about it at the bottom, maybe the right side, the left side? Hopefully you came into, wait a minute, the place where we model the system, we say we model the system as a point particle, and I'll put even further, located at the center of mass. So box, think of it, the point particle in the center. Car would be a point particle in the center of mass. Person, point particle maybe at their belly button. Okay. So I'd say, and go back and think about that, reflect on this. But essentially, when you're applying Newton's second law, you're doing this. You're modeling the system as a point particle located at the center of mass. Okay. So if that's what you're doing with Newton's second law, and our work kinetic energy theorem also comes directly as a consequence of Newton's second law, then the work kinetic energy theorem must also be modeling the motion of the particle, right? If Newton's second law applies to a point particle at the center of mass, then the work kinetic energy theorem must also be applied to a point particle located at the center of mass. Okay? So in other words, we are ignoring everything else about the system. And we'll see as we get into rotational motion, we will no longer model a system as simply a point particle at the center of mass. We'll model it as an extended, what I call an extended body. Okay. So to be continued with rotational motion, we'll do extended bodies, in other words, not point particles. So when we're talking about the change in kinetic energy, we need to be thinking about the change in kinetic energy of the point particle itself. Okay? Let me pause here for a second. So taking the analogy one step further, one step further, excuse me. So taking the analogy one step further, we could look at Newton's second law, and you remember I said it's a relation equation. It's relating observables to inferences. It's relating this acceleration that we can easily observe to these forces which we can't easily observe. Okay, so that's why I was saying it's a relationship equation. Down here, we have the same sort of relationship. Recall that the work is, again, just the interaction between the system and surroundings. Right? Going back and looking at our derivation, this work has a force in there. So this is describing the interactions. Here, This is the response of the system. Much like the acceleration is also the response of the system. So again, we actually have this interaction going on between system and surroundings. Now, this will be, excuse me, nose itch. This will be further expounded upon, but I'll give you the end goal here. Okay. The end goal is that this isn't the only naming game in town, but the full-blown equation that we'll see at some point is what I'll call the work external. So work done by the surroundings on the system. I'll call that the work external, plus what I will call Q. This will equal the change in energy of the system. Okay. Now that's further down the road. I'll explain the rest of it, but this is the first law of thermodynamics. Thermodynamics. Okay. And I'll say this is what we call the macroscopic work. In other words, the work done to change the particles, the motion of the center of mass of the particle. And I'll call this the microscopic work. Microscopic work. In other words, the work done on the individual atoms of the system. Okay. And generally, this is not usually referred to as microscopic work, but usually it's referred to as heat. Okay. So heat is an energy transfer process. And here, again, the energy of the system. So far, we've just been given the kinetic energy, but we'll soon see that there are other forms of energy aside from the kinetic energy. Okay? So this is the full-blown idea. Right now, we're just on this piece. Okay? Let's go ahead and get rid of the table. Get rid of that commentary. Okay. So let me pull it together for you, and then we'll keep going here. So we've already talked about forces, and I'll say, okay, well, net forces result in accelerations. Right? This is, you could say this is either Newton's first law, or if you're trying to quantify it, that's Newton's second law. Of course, accelerations mean that you have changes in speeds or velocities, right? If you have an acceleration, you have a change in velocity. And a change in velocity indicates that you have a change in kinetic energy. Okay. What I'll say is, pulling this all together, I'll say forces transfer energy. So again, this is why everything works. Aside from, I showed you how you can get it directly from Newton's second law, but conceptually what's going on is forces are how energy is transferred. Right? Forces are how, energy is the what. Okay? So how things are transferred and what is being transferred. And the idea is that we can either decide to look at how stuff is transferred, that would be the forces, or we can look at what is being transferred, the energy. And either way, we can come up with the same answer. The analogy I think of is something like a bank account. Okay? So if I think about bank accounts, bank accounts, I can think of keeping track of my balance in one of two ways. I can think of thinking about all the transfers. Oh, I've got a check that's been drawn, or oh, I've got a deposit being made, or I've, see an ATM pull out. Okay. I can think of how stuff is entering or leaving my bank account. And like I said, you can do a check, you can do withdrawals, you can do cash deposits, you can do cash withdrawals, etc. So I keep track of how things are moving in and out of my system. That's one way of doing it. So withdrawals and deposits. And if I keep, ideally speaking, if I keep track of all the withdrawals and the deposits in terms of transfers, then I know how much is in my bank account. Of course, the much simpler way of doing it is just look at the money, right? Keep track of how much has actually been in there or how much is gone. And so I think of, the analogy is I think of the withdrawal or the deposit process as being the forces, or I think of the total amount of money as being the energy. Either way is right. It's just that sometimes it's easier to think of problems in one way as versus the other. So the parting comments I'll make about energy, just as a general introduction, is I'm going to give you, I guess I'll say one rule, or maybe I'll say two rules. So there's two rules to the energy game. I'll say, and maybe you could say that this is just a single rule, but I'll say two rules to the energy game. Number one, the game is zero sum. Okay. And what does that mean? It means that there are always winners and losers. So a zero sum game means there's always winners and losers. Okay. What I mean by that is if you're playing a game and it always has a win and a loss, in other words, one person's victory comes at the expense of another person's loss, okay, that game is called zero sum. So you can think of games like musical chairs. I like thinking about musical chairs. There are no ties allowed. If one person gets a chair, that means that somebody else playing does not get a chair. And that's why we call it zero sum. There's winners and there's losers. The energy game is the same way. If an object has increased in energy, somewhere else another object has lost energy, whether that be an object in the system or another object in the surroundings. But you always have, if one gains energy, it has to have been lost somewhere else. So that's the number one rule. I'll say this could be a corollary to that. I'll call it a second rule. But the idea is energy cannot disappear. Okay. But I'll put in parentheses, it can change forms. Okay. So it cannot disappear, okay, but it can change its form. So we call that, well, yeah, I mean, that's the best I'll say right now. So what we'll do is, in the upcoming videos, we're going to take these two rules. We've already got an idea about work. We've got an idea about kinetic energy, but we'll use these two rules of the energy game to introduce a new form of energy, namely the potential energy. Okay? And we'll find out, at least immediately, we're actually going to introduce two forms of potential energy, one being gravitational potential energy and one being the spring potential energy. Okay? So I think that's it for right now. Thanks for your attention. I'll see you next time.